Today we're going to be talking about the power-reducing identities. The power-reducing identities are a direct result of the double angle formulas that we learned in the previous section. In this case, the double angle formulas that we'll specifically be looking at are the various forms of cosine 2x. So let's start by reviewing one of those forms. In our last video, we talked about the cosine of 2x, and we derived it in terms of why it has this quantity. So if you need to go back to that video, you can. But the cosine of 2x is equal to, in one of its forms, 1 minus 2 times the sine squared of x. And we got that through the sum and difference identities, as well as the use of some of the Pythagorean identities. In this case, what we'd like to do is solve this equation for sine squared x. So we want to isolate that sine squared x. In this case, to get the sine squared x by itself on the right side of the equation would mean that we would first need to get rid of this 1 that's in place. So we'll start by subtracting that 1 on both sides, which leaves us with the cosine of 2x minus 1 equals negative 2 times the sine squared of x. Okay, next thing that we want to do is get rid of the coefficient, that negative 2 that's placed on that sine squared x. In that case, because it is a coefficient, it's being multiplied by the sine squared, we're going to divide both sides by a negative 2. Now we're going to do something here that will require you to remember what happens to a subtraction problem when you divide by a negative. Ultimately, if we divide this difference of cosine 2x minus 1 by that negative 1 that's part of that negative 2, what it's going to do is reverse the two terms of that subtraction problem. So in this case, we're going to rewrite our numerator as 1 minus cosine 2x, all divided by a positive 2. So we've ultimately just divided both the numerator and denominator by a negative 1, or you can think of it another way as saying we factored a negative 1 out of the numerator and denominator and then canceled them. Now what we're left with on the right side is the sine squared of x. And this forms the power-reducing identity for sine squared. And it also gives us a chance to now talk about why they're called power-reducing identities. In a power-reducing identity, what you're doing is looking for a way to take an expression that has a power other than 1, a power of 2, a power of 3, etc., and find a way to simplify it. So these power-reducing identities specifically work on taking any quadratic expression, a sine squared, a cosine squared, or a tangent squared, and simplifying it down into something that is just a single linear type term where you have an exponent of 1. So here our quadratic expression of sine squared x becomes this expression where this cosine, although the angle is doubled, we had an x in the sine squared, here we have to recognize that that angle does get doubled, but that this term, this trig expression, the cosine of 2x, still has an exponent of 1. So it reduces the exponent, it reduces the power from a quadratic power down to a single power. But keep in mind, you have to remember to double your angle when you do that. Okay, let's look at another variation of this cosine 2x that we discovered or derived in the last section. Specifically in that case, we had the cosine of 2x is equal to 2 cosine squared of x minus 1. And in that case, we're going to do basically the same thing we did on the last one. We're going to try to isolate that quadratic term. In this case, we're going to try to isolate the cosine squared x. So here that will mean adding 1 to both sides. And I'm going to skip showing the intermediate steps on this one. So we add 1 on both sides. And then there again, we need to get rid of that coefficient, so we're going to divide by that positive 2 on both sides. And remember, it's everything on this left side that's divided by that positive 2. And this forms the power-reducing identity for a cosine squared. Here again, you'll notice that it involves a lot of similar structure in terms of how the cosine squared compares to the sine squared. They both involve a cosine of 2x. They both have this 1 They both have a division by 2. They're very similar, but the difference being that the terms in the first case in the sine are 1 minus that cosine 2x, whereas here in the numerator we have a 1 plus a cosine of 2x. Now you'll find that some books will, to keep that kind of format basically the same, they're going to write this numerator in this the cosine squared identity. Sorry about that. They're going to write that as a 1 plus cosine 2x, just so that it has a similar format here. But keep in mind that addition is commutative, so it won't matter which order we have this numerator in. It's the same regardless of the format that we use. That is not the case, though, with that sine squared. We have to have it as 1 minus the cosine of 2x. If you have those two terms reversed, then you're going to get the opposite of the answer that you need, and that's not what's necessary here. So remember that in the sine squared power reducing identity, your numerator is 1 minus cosine 2x, and in the cosine squared, it's going to be 1 plus cosine 2x. Okay, so then the question naturally becomes, well, what about tangent squared? Well, we know that by our quotient identities, that a tangent function is equal to a sine divided by a cosine. So in that case, if we kind of maintain the same idea, the tangent squared of x would be sine squared of x divided by cosine squared of x. And if you need some understanding as to why that works, remember a tangent squared is saying that you're taking the tangent of x times the tangent of x. If I change both of those into a sine x over cosine x and a sine x over cosine x, when I multiply those two together, that's where we're getting the sine squared x on the numerator and the cosine squared x on the denominator. Okay, so let's think about what's happening here. Another way to write this division problem is to write it with that traditional division symbol. We already have identified what the power-reducing identities for sine squared and cosine squared are. Those are the ones that we've derived here. So in this case with sine squared, we have this quantity, this fraction. And in the cosine squared, we have this fraction. If I were to write it as a division problem, I could do that here by just substituting these quantities in place of this first fraction. But I want to look at it here so we can review what happens when you divide with fractions. Okay, so we're going to replace this sine squared with this quantity that we derived earlier, 1 minus cosine 2x all over 2. And we're dividing that by the cosine squared, which is this quantity, cosine 2x plus 1. There again, if you wrote it as 1 plus cosine 2x, that's fine, all divided by 2. Now, when it comes to dividing fractions, we know that to divide two fractions means you keep the first fraction the way it is and multiply by the reciprocal of the second. So in this case, that would look like this first fraction, 1 minus cosine 2x all over 2, times the reciprocal of the other, 2 over, and I'm going to go ahead and reverse those terms, 1 plus cosine 2x. Okay, so now we can do one of two things. We could multiply straight across the numerator, multiply straight across the denominator, and then simplify. Or, because it's all multiplication and division, we can start canceling some common terms, or common factors. In this case, the factors that we have in common, one in the numerator and in the denominator, is that quantity 2. So here, if we cancel out this 2, cancel it out with that 2, basically we're identifying that that 2 over 2 is equal to 1, and therefore just reducing it. In that case, what we're left with is the quantity 1 minus cosine 2x over the quantity 1 plus the cosine of 2x. And that is your power-reducing identity for a tangent squared. It takes that exponent of 2 and simplifies it into an expression where the exponent is 1 in both the numerator and denominator. And that takes care of your power-reducing identities and how they are derived from the cosine of 2x formulas that we got in the double angle formulas in the last video.